Okay, so I think we're just about ready to get started. So first of all, thanks everyone for joining us for this seminar of the Working Group on Active B stars. So we're restarting our monthly seminars this month and going all the way through to next May. So we're very lucky to have Dr. Julieta Sánchez Arias joining us from the Czech Academy of Sciences. So Dr. Sánchez Arias did her PhD at the University of La Plata, and then did a first postdoc at CONICET in Argentina before moving across the pond and doing a second postdoc at the Czech Academy of Sciences. So we're very happy to have Dr. Sánchez Arias talking to us about the evolutionary state of B supergiants today. And with that being said, thank you, Dr. Sánchez Arias, for joining us, and I will pass it on to you.
Okay, thank you very much for joining. I would like to talk in this seminar about the evolutionary state of 3 B supergiants. And this is a work that I developed with Peter Nemeth, Elison de Almeida, Matthias Ruiz, Michaela Kraus, and Maximiliano Hauke. And it was developed in the frame of the Poems project from the Marie Curie funding by the European Union and led by Michaela Kraus. So these supergiant stars are massive stars. They show effective temperatures between 10,000 kelvins to 30,000 kelvins. The luminosity is between 10 to 4 to 10 to 6 solar luminosities, and they have a mass loss rate between 10 to -7 to 10 to -5 solar masses per year. This is an HR diagram with different massive stars. We have in the hot part of the diagram the Wolf-Rayet stars, and following by the blue supergiant stars, which are our objects, and depicted with blue stars. Also the LBB stars, and then we have yellow hypergiants, and finally the red supergiant objects. These B supergiant stars show a spectroscopic variation related to WIMP's variability. Until 985, and they thought to be hydrogen shell-burning objects and evolving towards the red supergiant stage. But in this year, one of these objects exploded as a supernova. So we currently know that these stars can lie in the pre- and post-red supergiant stage. The physical properties of massive stars change considerably within each stage of their life. The evolutionary tracks depends on many physical parameters, such as the mass loss rate, the rotation, the chemical mixing. We can see in this plot, for example, an evolutionary track of 15 solar masses with and without overshooting, and how the overshooting affect or produce a blue loop towards the hot part of the diagram. And in the lower part, we can see how different mass loss prescription over the evolution affect the end of the massive stars. For example, this is the 15 solar masses at the 0H main sequence, and is evolved until the onset of the core collapse, and we can see that different prescription leads to different surface chemical composition as well as different masses. So we can see that these stars evolve towards the red supergiant stage and back to the blue part of the HR diagram at mostly the same luminosity. This might difficult the access of the evolutionary stage. So luckily, some of them oscillate, and this is an interesting work performed by Sayo and collaborators in 2013. and which shows that stars at the post-red supergiant stage exhibit much more oscillation in comparison with stages at the before the red supergiant stage. These B supergiant also oscillate in radial and non-radial modes, driven by the kappa mechanism, and also driven by convective surface layers, which are stochastic modes. They also show further light curve variations due to wind variabilities. So it's difficult to distinguish one from the other one. And I have to mention that it also has been proposed as a mechanism for the mass loss and strange modes. I am not an expertise on strange modes, but I would like to mention that in order to study them, it is needed to follow the instability of these modes through nonlinear regimes in order to compare the pulsation velocity of the modes and with the escape velocity of the stars to see if the excited mode can actually derive mass loss and mass loss. Also, I would like to mention that after the red supergiant stage, blue supergiants lost a lot of mass, so it's easy to find them at very high luminosity over mass radius, and this is a very highly non-adiabatic environment in which many of the oscillation codes fail to reproduce correctly or precise the non-adiabatic modes. So in this work, we combined the analysis of photometry, spectroscopy, and also evolutionary models, and in order to have comprehensive pictures of blue supergiant stars, we started selecting 3 objects for which we have unpublished observations. And the objects are HD 42087, which has the higher luminosity. Also HD 58350, HD 52s and HD 52089. This object has been extensively studied in the literature, and in the most recently study for them is the one of Hauke and collaborators 2018. And in this table, I am showing the parameters that this work and these colleagues derived for these objects, which are the ones depicted in the HR diagram. So over literature, we found for this object many different parameters, values for these parameters, and might be related with different methodologies and also different observation over time. And they have variable mass loss rate and variable radiative, and also they have variations in the light curve. So, one second. So for the observation, we use the Rios spectroscopy attached to the Jorge Sade 2.15 meters telescope at the Complejo Astronómico Leoncito, CASLEO in San Juan, Argentina. We cover a range of 4,275 angstrom to 6,800 angstrom, and with a resolution of 12,600 and 13,900 at 4,500 and 6,500 respectively. In this figure, we show the H-alpha line profile for the different observations that we have gathered with this telescope over the years. And we can see that for HD 42 and HD 58, and they show a very wind and a wind variation in their profile. So for study the photometry, we use the TESS high cadence light curves, and in order to perform the selection criteria for the frequencies, we adopt them, and then in order to select the frequencies, we adopted the next selection criteria. We search for periods between 0 and 15 cycles per day, and we work with the residuals after deriving each frequencies in a pre-widening procedure. And we dismiss those frequencies below 0.1 cycles per day for single sectors. And we discard also those frequencies with a separation less than 2 times the Rayleigh frequency. And also we use as the signal to noise and the values recommended by Baran and Cohen in 2021. So the frequency analysis for HD 42, this object has been observed for 3 consecutive sectors, which allow us to obtain a very low frequency for the combination of these, for all the sectors combined, and of 0.093 cycles per day, which corresponds to a period of 10 days approximately. And we have found the harmonics of this frequency in each of the sectors. And also we can see that the light curves display erratic behavior, and besides the harmonics of this frequency, low frequency, we detected also 5 independent frequencies which are likely related to a stochastic variation. For the frequency analysis of HD 52, and this object has been observed for 2 consecutive sectors separated by 2 years of time. And we found many stochastic frequencies which are randomly excited over the sectors. And also for sector 33, and we measure the differences between F2, F4, and F3. And we believe that this is possibly a rotational splitted center and F2, suggesting a rotational period of 5 days. And for the frequency analysis of HD 58, and we has been observed only in 1 sector, and we derive it in 2 independent frequencies, but we will need more observations and in order to determine the nature of these frequencies. For the spectral analysis, we have used CMFGEN in order to model the atmospheres of our stars, and under the assumption of radiative equilibrium and spherical symmetric and stationary winds. And this is a non-LTE radiative transfer codes, which allows to set a complex chemical composition with the inclusion of energy levels for different ions, up to nickel. And it also assumes a beta low velocity profile for the wind, and it works fine for stars close to the Eddington luminosity. For the fitting procedure, we use XTGRID, which is an iterative global spectral analysis procedure, and that has been developed by Peter Nemeth, and to study white dwarf and hot subdwarf stars with LTE. And in this occasion, he updated the procedure in order to include CMFGEN and to study these objects with wind variabilities for the first time. So we made some assumptions, and in order to start the procedure for the spectra, and which was to keep fixed the radii, the turbulent velocity, the microturbulence, and the beta coefficient, and the terminal velocity, as in Hauke and collaborators 2018, and we adapted no clamping. All the elements except the CNO, which were the elements that we are interested in derived, were kept fixed to solar abundances. And we also adopted a ratio between helium and hydrogen equal to 0.2 as in early 2008. This is the result of the fitting procedure. The black curve is our model. The gray curve indicates the observation spectra, and the red is the residuals of the fitting. We could derive many parameters for all the stars, and as the effective temperature, the log G, and the mass loss rate, luminosity, mass, radii, and also the surface abundances for the three of these objects. We can see in the figure the H-alpha line, carbon lines, and H-beta as well, and silicon. So in order to compare the results with evolutionary models, we consider those models from Ekstrom and collaborator from 2012, which has a central hydrogen concentration of 0.2, and for the helium 0.6, and also a solar metallicity of 0.014. We adopted two different shell rotations of 0.568 and 0.4. The differential rotation of 0.4 was derived by an interpolation between no velocity and the maximum velocity of 0.568. And these models adopted the mass loss recipe of Bing 2001 and the Jager to 1988. So for HD 42, our values of effective temperature and luminosity suggest an initial mass of 26 solar masses, and the current mass of 24.3 solar masses that we derived indicate that this star is at the pre-red supergiant stage. And in this figure, we plot the HR diagram above and the evolution of the mass in the lower panel. And in comparison with literature, this value for the effective temperature is higher, and the log G is lower than Searle and Hauke. But I would like to mention that in Hauke and collaborators, the silicon lines were not considered to derive the effective temperatures. So we trust in our values. And in order to check our parameters derived with CMFGEN, we compare the theoretical SED with the observed data, photometric data. And we can find for adopting Gaia, the distance from Gaia data release 3, and also an extinction of 0.4, and that our measurements, the theoretical SED fit the observations, and also the mass derived from the SED is 22.5 solar masses, which matches our mass derived with the CMFGEN mass. But we were unable for this star to fit the H-alpha line and also the H-beta. And we suspect that this is due to asymmetries that has been reported in the wind And so our steady, smooth, and symmetric model for the wind will not be the correct one to use. And also we found mass loss for this object and higher and lower than the one found in Hauke et al. But this could be consistent with a stronger emission for the observations for the previously observation. For the frequency analysis of this object, we see that there are 5 frequencies that appear randomly over the sectors, and the short lifetime of these the frequencies prevent us to associate them with stellar oscillations, but rather with a stochastic oscillation at the surface and possibly connected with wind variations. And as I mentioned before, we found a very low frequency corresponded to 10 days, which has an uncertain origin. And we could not find a frequency associated with the period of the variation of H alpha line that other authors have found before. And also the lack of multiple stellar pulsation modes would suggest that this star is at the pre-red supergiant stage, which is in agreement with our values for the current mass and the luminosity. For HD 52, the new values for the effective temperatures and luminosity suggest an initial mass between 12 and 14 solar masses. And the current mass of 12 solar masses indicate that this star is at the terminal H-main sequence. And in comparison with literature, we found a discrepancy between the mass, the luminosity, and the effective gravity. And it also that also has been detected in Hauke and collaborators. We have compared the theoretical spectral energy distribution with the photometric observations. And this object is very close to us and has a very short distance. And with that distance and a moderate extinction, we found a good agreement between the mass derived from the SET of 9.8 solar masses and the mass derived with CMFGEN. And we can see that the slope from our theoretical SET matches the IUE observations, but there is an offset, maybe related with the metallicity. And our derived mass loss rate agree with the one reported by Hauke and collaborators in 2018. For the frequency analysis, we found a possible triplet in one of the sectors, which indicate, considering the radius of the stars, a rotation of 110 kilometers per second, which match this NI value derived for this object, considering an inclination of 20 degrees. And this frequency appears in all of the sectors except for sector 1, but there are some features that indicates a lower amplitude for this frequency, and this could support the idea that is a non-radial oscillation mode. And also we have found a stochastic low frequency variability in frequencies, in 3 frequencies. For HD 58, We have found an excellent agreement between the effective temperature and the luminosity and the current mass with evolutionary models that suggest that this star is at the post-red supergiant stage after losing considerable amount of mass. I would like to mention that we have found many different values which rank from 13,000 and up to 16,000 kelvins for the effective temperature. And and due to the marked H-alpha line profile variation in this object, and we believe that the only two frequencies spotted for these stars might be related to wind variabilities. And also, I would like to mention that we could not detect the period corresponding to 0.15 cycles per day, detected in Lefebvre et al. In 2007, which might indicate that this period is related to wind variabilities. And we have compared also this result with the SCD, and we found that the optical observation fit and the theoretical curve, and we found also that there is a slightly different slope for the infrared data, and which we believe might be related to different time observation for this data with our spectra. And we could we adopted the Gaia data release distance, and we derived an extinction for this object of 0.18 magnitudes. And we also found discrepancies between the theoretical curve with the SCD and the CMFGEN mass. And our value for the mass lost is lower than the one in Hauke and collaborators 2018, which is in agreement with the weaker emission component for the H-alpha. So what about the surface abundances? We have found a mild overabundance of nitrogen for our 3 stars in comparison with the sun, and also a slightly depletion of carbon and oxygen, also compared with solar abundance. These trends fit the trends found by Shirley and collaborators, which is the pink curve in this figure. But we have found higher values for the carbon and lower values for the oxygen, and we compare with this work performed by Shirley and collaborators 2008. In order to continue or to have a broader view about what is happening with the surface abundances, we perform or we plot these figures, and in which in the higher panel, and we marked the nitrogen over oxygen abundances against the effective temperature, and the nitrogen over carbon abundances in the lower panel. We also included in this figure 3 samples. One sample from Georgia 2021 and with blue dots, Shirley 2008 with red squares, and a sample of Lyubimkov 2013, which corresponds to main sequence stars. So in this figure, and we can see 3 defined groups. The group of main sequence stars with triangles and brasses lower and over O and over C abundances. And we also can see compact group at lower temperatures, and below 3000 kelvins, and hot and more scattered supergiants and above 15,000 kelvins. And these samples is a sample of A and B supergiant stars. And we also can see that none of the measurements of the considered samples fit or reach the predicted abundance for the carbon and oxygen at the post-red supergiant stage. Also, we can observe that our abundances for the 3 stars corresponds to evolutionary stage at the pre-red supergiant phases, and this is in contradiction for the object of for HD 58, and for which we have derived according to the luminosity and effective temperature and the current mass that is an object at the post-red supergiant. This inconsistency in between the evolutionary stage and the surface abundances has been spotted by SAIO for Rigel and the Neve stars, and we believe those are interesting objects to study further. And in this plot, we have compared the nitrogen over oxygen abundance against the nitrogen over carbon abundances. And we also include the same sample of stars and our objects. And we can see that our stars lie below the sample of the evolutionary tracks. And also we see that the Georgi sample would fit better the evolutionary tracks for Ekstrom and collaborators. And the sample from Searle is more a scattered one. And we also see that there is a systematic carbon underestimation and oxygen overestimation for all of these stars. So as a conclusion, we combined in this work spectroscopy, photometry, and evolutionary models to study blue supergiant stars. We need to study homogeneously a larger sample of B supergiant stars in order to analyze the systematic offset in the carbon-nitrogen abundances, oxygen abundances. We also need multi-epoch observations to set constraints and to study the variations in the radiative and effective temperatures due to stellar oscillations. We need to consider, and it could be wise to consider that a stellar oscillation can be a mechanism to facilitate the mass loss over the evolution and affect the surface abundances. And we also need to gather long-term photometric observation to detect oscillation modes and that facilitate the mass loss, and which usually are between 10 days and 100 days. To develop non-linear oscillation codes in order to study mass loss due to stellar oscillations, and to maybe possibly review the burning ratios of the CNO cycle in evolutionary models, and to test further and maybe improve the solution for non-adiabatic stellar oscillations in highly non-adiabatic stars as this one. That would be all. Thank you very much for your attention. And I would like to, again, thanks to Michaela and her project. And it's a very big project in which many countries are participating, many of them with very difficult situations. And it allows the exchange of students from different countries, and thanks to it, we can we could give this first step toward the study of these objects. So thank you very much.
All right, thank you very much, Dr. Sánchez Arias, for this interesting talk. I think on behalf of everyone, I would like to thank you. So at this point, I guess we'll take questions. So I see a hand raised for Doug Guys. Go ahead, Doug.
Hello, Julieta. Thank you very much. Very nice talk and congratulations on this good work.
Thank you.
I wanted to make one advertisement and then I had one question.
Please.
My advertisement is that two of your stars, 58350 and 52089, Eta Canis Majoris and Epsilon Canis Majoris, are stars that are both resolvable with the Chara array interferometer, so that you can actually measure the angular diameter of those stars directly from the visible band through the near infrared. And then combined with the Gaia distance, you'll be able to get a direct measurement of the radius of the stars in 3 bands. And it would be very interesting to compare those radii with the radii that you're getting and for example, the predictions from the CMFGEN. So you might want to consider that as some future, if you have time or interest. It's
yes.
The telescope.
Thank you very much.
It's available to the whole community. Anyone can apply through the US NUAR lab for observing time, and it's now pretty easy to do. So that might be something of interest. My one question for you was about Epsilon CMA 52089. This was a very famous star back in the 90s and was observed by Joe Casanelli in 1996 and David Cohen later in 98 in the extreme ultraviolet, very low wavelength, between 600 and 900 angstroms. And I was wondering if you'd had an opportunity to compare your model SED with those observations down at very small wavelengths, 600 to 900 angstroms.
No, we only compare it with the IUV observations, and actually we found that there is an offset between the theoretical SED and these observations. I'm not sure what can we found with those. In which year have been taken those observations?
Yes, they were made back in the early 1990s with a NASA mission called the Extreme Ultraviolet Explorer, and then another mission called Orpheus. And there was a lot of controversy about them because, well, most O stars and B stars are so far away that they're behind a screen of interstellar hydrogen. And so you don't see them at all at extreme ultraviolet wavelengths because the interstellar medium is too opaque. But this star is the exception. You can actually see it because there's a local hole in the interstellar bubble around the sun in the galaxy. So you can actually measure the extreme ultraviolet flux of this star. So maybe something for the future you might be interested in exploring.
Yes, thank you very much for the recommendation. We will take it into account.
Okay, see Joe.
1 second. So can you hear me? Yeah. Okay. So Julieta, thanks a lot for this very informative and very nice overview and your work that you have done. I had originally 3 points, but 1 point was mentioned already by just before, namely the comparison to this EUVE satellite, which might be very interesting. So that's something what you can do easily. So my other 2 questions are the following. At first, I do not completely understand why you have fixed the helium abundance at 20%. Was this a time problem, calculation time, modeling? And so the question is, have you at least checked whether this is in the correct ballpark? This is my question number 1. And my question number 2 would be, certainly you have a slide where you have compared your results with the final results also from Hauke and collaborators, so that one sees whether they are overlapping within the errors or whether there are certain things which are really discrepant.
So for the first question, yes, it is a little bit higher than it's supposed to be, the fixed value. And we adopted following this is our first work working with this type of stars. And I have to say that I would like to thank the referee extremely a lot, because we learned many things. And one of the main reasons to fix that value was the time and to dealing with deadlines. It took many days to reach a fit solution for the spectroscopy. And the second one, could you please repeat me the second question?
The second question was, do you have some, or can you simply tell us whether when you compare the results which you have derived here, particularly effective temperature and log G and so on, when you compare this to the Hauke results, whether they are overlapping within the errors or whether there are really big discrepancies concerning specific quantities? Now, not speaking about the mass loss, of course.
I can show the plots for the, yes.
You certainly have done this by yourself, I guess.
Yes. We found better constraint values for the errors of the effective temperatures and this for these stars. And this is the HR diagram for the three of our stars with the values derived, and we can see here the obtained values for our fitting procedure. So there are some discrepancies, but it doesn't seem too big discrepancies, but the most remarkable things was to find lower values for the errors in the effective temperature and effective and luminosity of these stars.
So this is clear because you had also the silicon lines, whereas Hauke did not use the silicon lines, and they are the best indicators, of course, in this temperature regime. Okay, thank you.
Yeah.
Okay, are there any other questions for Dr. Sánchez Arias? Okay, I might use my prerogative here. Just thank you for a very nice talk, first of all. And just one question. I'm sorry if I missed it, but you were talking about obviously the differences in mass loss rate between different epochs. Can you comment on the quantitative, a bit more quantitatively on kind of the amplitude of that change that you see?
The amplitude of the change of the mass loss, or let me check. There is a big problem, and in order to assess the different values for the mass loss rate and in these stars, mainly because they have been taken in different times. And yes, we found the biggest discrepancy in the mass loss, and I believe for HD 5042, and which is depicted in this figure. And yes, I'm not sure how much would you like me to expand on this too? But
that's okay. We can have a further discussion.
I have to say that
I was just wondering, because I know that there's also
I have to say that in this work we combined many different skills from all of the co-authors, and I am working mostly in evolutionary models and asteroseismology, and Peter and Ellison have worked mostly in the spectroscopic part to derive the fitting. procedures, and we are very happy to have this collaboration because we can make like a decent approach and to study and combining this different knowledge for this star. So yes, maybe Peter can extend on this matter, or I don't know.
Can you hear me? It's Peter.
Yes.
I also cannot answer that question because we work on different spectra from different years, and what we fitted within this project and how the spectral fits reacted to different mass loss rates. It's hard to estimate, but I think it's a factor of 2 or 3 that we can have in the mass loss rates, that kind of variation. But we need to process many spectra from different times, years, to see what is the true variation in the mass loss rate.
Okay, thank you. Yeah, that's very interesting because I'll just point out quickly that recent studies by David Cohen show that for Zeta Pup, which is an O supergiant, depending on how you interpret variations in the X-ray properties, you might infer changes in the mass loss rate, or at the very least in the wind structure, that are quite substantial, on the order of like 40%. So it sounds like maybe this is something to be investigated further, how the winds of supergiants can change over timescales of years to decades. So yeah, thank you very much.
Yes, and certainly we need to remove all these fixed parameters. So we need to fit everything, also observe clumping and such effects, because these all have small additional effects on the mass loss rates, abundances. So we work towards that solution.
Great, thank you. Are there any more questions for Dr. Sánchez Arias? We still have quite a bit of time if people would like to ask some more questions. Okay, in that case, let me thank Dr. Sánchez Arias once more for a really nice talk and obviously some very nice work.
Thank you very much for the opportunity. I really appreciate it.
We're very glad to have you. And for everyone, I will mention that there will be another seminar next month, of course, for the third Tuesday or Wednesday of the month, as usual. So just stay posted, and we will send the details for that shortly. So thanks again, everyone, for attending. Thank you, Dr. Sánchez Arias, for this very nice talk.
Thank you.
And I'll see you all pretty soon.
Okay, goodbye. Thank you.